Hi guys, can you guys hear me?
Yes.
Okay. All right. I'm going to wait a few more minutes before I start the class, okay? Okay. All right, I'm going to continue chapter 17 before I start chapter 19 today. Last time I stopped at explaining the complex ion formation. I'm going to explain this one more time. So the third factor that affects the solubility of a substance is formation of complex ion. Okay. A characteristic property of metal ions is that they can act as Lewis acids. Okay. And with Lewis base in the solvent. So, for example, let's say you have insoluble or slightly soluble silver chloride salt, tiny in aqueous solution. Tiny amount of this salt that dissolves in water will dissociate into silver and chloride ions, right? And let's say you're adding aqueous ammonia solution into the system. So you have a silver chloride in the water and you are adding aqueous ammonia solution into the system. What's going to happen? What's going to happen is that ammonia act as a Lewis base and silver metal ion act as Lewis acid and they will react. Due to this reaction, which ion is going to be disappearing? Because ammonia is reacting with silver, silver ion is going to disappear throughout the time. So then what happens if silver ion concentration goes down? The equilibrium will shift to the right. Because you are depleting this, the equilibrium will shift to the right in order to produce more of what's getting disappearing. So because the equilibrium is shifting to the right, silver chloride will be more soluble and will increase in solubility. The resulting ions from this reaction between metal ion and the Lewis metal ions as a Lewis acid and Lewis base, this resulting ions is called complex ions. And here are the list of complex ions. And again, the formation of complex ions, they are all also soluble in water. These complex ions are also soluble in water. So they will have the equilibrium constant as well and denoted as Kf. we have learned so many different the equilibrium constants so far. We've learned about Kc, we've learned Kp, Kw, Ksp, Kf. You should be able to distinguish all of these equilibrium constants for the final exam. Okay?
Professor,
Uh-huh.
do we have to memorize those charts?
No, no.
Okay, thank you.
Mhm. Okay. So that's that. And then let me briefly introduce what amphoterism is. Okay. So some metal oxides and hydroxides that are relatively insoluble in water can dissolve in both strong acids and strong bases. Okay. So strong acid or strong bases. Okay. Mm. So metal oxides or hydroxides that are relatively insoluble in water, being soluble in strong acids and strong bases. These examples, these metal oxides are special because they can act as both acids and bases. Okay, they can act as both acids and bases. Okay, and the examples of oxides and hydroxides of these only. Okay, these only will be amphoteric. Okay, so oxides and hydroxides of aluminum, oxides and hydroxides of chromium, oxides and hydroxides of zinc, tin, they will be they're relatively insoluble in water, but they will be soluble in strong acids and strong bases. Why? Because they can act as both acids or bases. You do not have to memorize anything from this amphoterism slide. I'm just briefly introducing to you that there's such a thing. So, yep, they have. So these metals, oxides and hydroxides, have special properties. Act as both acids and bases. Okay, here's an example. So, aluminum hydroxide. Aluminum hydroxide is amphoteric because it can act as a base and it can also act as acid. Okay, in case it's acting as a base, what's going to happen is that when aluminum hydroxide act as a base, you will react with any acid that is added to the system. Okay, and then reduce the hydroxide concentration. So as you can see here, if you aluminum hydroxide dissolves in strong acid, it will react with any acid in the system. Okay, and then it will form aluminum and water. Okay, aluminum hydroxide can also act as an acid. It will react with any base within the system, okay, and then reduce the aluminum concentration and generate this. Before wrapping up this chapter, we will learn about another type of problem where two soluble salts react with each other and generate insoluble salts through ion exchange. So let's say you are mixing Let's say you're mixing these two solids, okay? And predict what's going to happen. First of all, according to the solubility table, these two salts are soluble salts. Okay, these are both soluble salts. Between these, and then can you guys I'm not sure if you guys can recall the meta-thesis reaction from General Chemistry 1 class, but meta-thesis reaction is basically exchange reaction. So if these two salts exchange cations and anions with each other, you will be generating lead sulfate and sodium nitrate. And between these salts, sodium nitrate is a soluble salt according to the, soluble salt according to the solubility chart, but this lead sulfate is insoluble salt according to the solubility table. Okay, so in order to determine whether lead sulfate is going to be precipitated or not, you need to calculate the reaction quotient Q. Okay, and compare it to the solubility product constant of the lead sulfate. Where do you find this information? Back of the book, right? So the KSP value for lead sulfate it's a published value. It's known to be 6.3 times 10 to the negative 7. Okay, so if Q value is smaller than this KSP value, which is 6.3 times 10 to the negative 7, what's going to happen is that more lead sulfate can be dissolved. There is no precipitate yet. If the reaction quotient Q value is higher than KSP, this means no more lead sulfate can be dissolved. There is precipitate. Precipitate will form. What about Q equals KSP? This indicates a system where the system is at equilibrium and the solution is max saturated where no more solid can dissolve. Okay. Let's try a sample exercise. I'm going to bring the solubility table down here. Sorry, it's loading. Okay, is it clear for you guys now?
Yes.
Okay, all right. I don't think I can bring the solubility table down, but again, solubility table, you can find it in slide. I think back in slide for slide 40 or 41 or something like that. Okay, so a solubility table is contained in the previous slide, or solubility table is table 4.1 from textbook. Okay. You do not have to memorize anything from the solubility table. If in the final exam or exam 3 ask any question regarding the solubility, the table will be provided to you. Okay, so let's try the sample exercise. Does a precipitate form when 0.1 liter of 8 times 10 to negative 3 molar lead nitrate is added to 0.4 liter of 5.0 times 10 to negative 3 molar of sodium oxide? Okay, so this is a reaction between, oh, not sodium oxide, I'm sorry. This is sodium sulfate. Okay, can you guys please fix that? Sodium sulfate. Okay, so this is a reaction between lead nitrate and sodium sulfate. Okay, and then according to the solubility table, these two are soluble salts. Okay. The metathesis reaction between these two salts are going to form sodium nitrate, a soluble salt, and lead sulfate. Okay, so in order to determine whether this precipitate, in order to determine whether precipitate of lead sulfate will form or not, we need to compare the Q versus KSP. Okay, so to determine whether precipitate will form or not, need to compare Q versus KSP. So again, the KSP value of the lead sulfate is back of the book. We know that it's 6.3 times 10 to the negative 7. Okay. And let's find the Q value of lead sulfate. Okay, so how do we find Q? We know the KSP value. How do we find Q? Okay. We're going to find the Q value. All right, so let's say, although lead sulfate is an insoluble salt, a tiny, tiny, tiny bit of amount of this will dissociate into these ions. In order to find the reaction quotient Q, we need to determine the concentration of lead and sulfate ions. Okay, so the amount of mole of lead would be whatever amount of mole of lead nitrate dissolved in the aqueous solution So the number of mole of lead nitrate dissolved in system was given as this. So that means because this amount of lead nitrate dissolved in the aqueous system, the maximum amount of lead that you can get is this much, because you're getting the lead from this salt dissolving in water. Okay, so the mole of lead ion equals to mole of lead nitrate in the system, okay, which equals to, this is given in molarity, so you need to convert in mole, right? So which is equals to 0.1 liter times 8 times 0, 8.0 times 10 to the negative 3 mole per liter equals to 8.0 times 10 to the negative 4 mole. Okay, so as for the sulfate, where do you get the sulfate? You got sulfate from sodium sulfate here. So whatever the amount of mole you have of sodium sulfate you have in the system is going to be the mole for the sodium sulfate. So number of mole for sodium sulfate, for the sulfate ion is going to be mole for the sodium sulfate salt, which equals to 0.4 liter times molarity 5.0 times 10 to the negative 3 mole per liter equals to 2.0 times 10 to the negative 3 mole. Okay, so now we have mole of lead and mole of sulfate. We can calculate the concentration of these ions. So the concentration of the lead is equals to mole divided by total volume. Okay, so the mole is, we have here 8.0 times 10 to the negative 4 mole divided by the total volume in the system. You have 0.1 liter plus 0.4 liter, so the total volume in the system is now 0.5 liter. So this gives a concentration of 1.6 times 10 to the negative 3 molar. As for the sulfate concentration, you have 2.0 times 10 to the negative 3 mole divided by total volume equals to 2.0 times 10 to the negative 3. Oops, sorry. 4.0 times 10 to the negative 3 molar. Okay, so now you have concentration of lead, concentration of sulfate ions. We can finally calculate the Q, the quotient. Okay, so the quotient is going to be.
Can you pause right here, please?
Mm-hmm. Can I continue?
Yeah, you can. Go ahead.
Okay, so how do you find reaction quotient Q? Reaction quotient Q is going to be product concentrations divided by reactant concentration, right? But reactant is in solid form, so are you going to include that or no? No, right? So the reaction quotient Q is basically concentration of lead, concentration of sulfate. That's it. You don't divide by the concentration of lead sulfate because it's solid, okay? So the reaction quotient Q is concentration of lead times concentration of sulfate. Multiply these two values you get 6.4 times 10 to the negative 6. Okay, all right, so now we have K and Q value. Let's compare that. Okay, because KSP is 6.3 times 10 to the negative 7. Q is 6.4 times 10 to the negative 6. Which one is larger? Q is larger, okay? Q is larger than KSP. So then will precipitate form? According to the previous slide, when Q is larger than KSP, the precipitate forms, right? So lead sulfate will will precipitate. Okay, so that's that for chapter 17. We're going to skip last 3 slides. Okay. So again, this solubility part is going to be included in exam 3 and final exam. Okay. All right. So that's that for chapter 17. I want to quickly talk about the extra credit and the exam corrections that you guys did. Okay, so how many people we have here today? We have about 38 students here, and I remember, if I remember correctly, during last class we also had about 40 students, and that was it. But then I only announced about the exam correction in the class to that 40 students, but miraculously about 65 students did the exam correction. Okay, so the students spread the word. That's totally fine. But I intentionally did not announce in the announcement section because I wanted to give that opportunity to students who regularly attend the lecture, who really pay attention to the lecture, and who actually care about this course. Okay, so yeah, more than I had to grade more than I expected, but that's totally fine. But try not to, if you missed last lecture and if you attended this lecture, try not to miss the lecture, because students who don't attend the lecture and hear these extra credit announcement or exam corrections announcement from their peer students, they tend to come to me and ask very, very weird questions through email. And I was suffering from receiving so many emails and questions about the exam corrections because they didn't attend the lecture. They didn't listen to the announcement directly from me. They had no idea what was going on. So they were just attacking me with questions through email. So I was suffering. Okay. So try to attend the lecture. Okay. And try to get as much information as possible directly from me. Okay. So as for the extra credit for study guides, I was very impressed with few of the students, and I was very disappointed with a few of the students as well. Okay, so I could, for very few of the students, I could tell that they just made the study guide just to get the extra credit. But giving out extra credits was not my purpose. I wanted you guys to develop a study good study method to be prepared for the exam, prepare for the final exam. Okay, and making a study guide was a good study method technique for myself. So that's why I recommended you guys to prepare one. Okay, but and then I saw a good correlation between students who prepare good study guide and high exam scores. There was a clear correlation. Okay, so I took a look at study guides for a few students who got A for exam 2. Their study guides were amazing. Okay, so I know you guys have a group chat on Discord or wherever, I'm not sure, but if you scored high score on the exam, if you have good study guide, I think it will be very beneficial to share that study guide with other students so they can learn from you. Okay, so or if you know a friend who got high score on the exam, try to reach out to them and then try to see if you can get access to their study guide and use their study guide to make your own study guide. Okay. So, yeah, study guide shouldn't be just a piece of paper consists of equations. That's not study guide. That's the equation sheet. Study guide should be thorough, detailed. Okay. My version study guide is still not enough. Okay. You should include more examples, more notes, and more detail into the study guide than what I prepared. Okay, so for exam 3, try your best to prepare a good version of study guide. Your study guide should be the only source that you use to study for the final exam. It should be that detailed. Okay, so prepare a detailed study guide so that you don't need any other source, any other materials to study for your final exam. Okay, so that level of study guide was what I was expecting, but maybe there was miscommunication. Maybe students were just rushing, making a study guide just to get the extra credit. A lot of the study guides were very short, brief, and it was really disappointing for me because I didn't create this extra credit assignment just to give out the 5 points. I really wanted to encourage you guys and develop a good study method for you guys. Okay. And then some students were asking me if they prepare a good version of study guide right now and then submit it to me, if I can regrade or not. So as of whatever's, I'm going to grade whatever submitted until last Sunday, March 27th. Anything submitted after that, I'm not going to grade because regrading requires a lot of time. So grading your study guide and exam corrections for each student took me about 30 minutes, okay? And can you multiply that to 65 students? That was a lot of work for me, okay? But so I physically don't have enough time and energy to regrade any resubmission. So I'm sorry, but I'm not going to regrade any resubmission of exam correction or study guide at this moment. And then as for the exam correction, I really want to hear from you guys. Was it effective? Okay, so I didn't allow you guys to do exam correction just for you to get higher grade. I really wanted to. The purpose was to help you understand exam 2 material better. Okay, so like as I promised last time, this Friday I'll be on campus from 10 a.m. through 1 p.m. I will announce the exact time on Thursday. So around that time, I will be on campus. If you can stop by, I will be in the Chemistry Learning Center, 2nd floor, the computer room. Okay, you can stop by. You can, if there was any question that you're still struggling after doing the exam correction, this is a good time we can have a one-on-one conversation. Or if you just want to have a quick chat about future study method or anything related to the course, you can stop by and have a quick chat with me. That's fine too. Okay, so on Friday I'll be on campus, and then I would really like to hear feedback from you about what do you think about doing this exam correction. Was it really helpful for you to understand the exam 2 material better? Okay. And then another thing I wanted to say is that do not really focus on getting higher grade. Okay, passing this course is not the end. Okay, if you don't develop right and effective way of studying, you will struggle in the upper division chemistry courses. So as a general chemistry instructor, I have a mission to get you guys well prepared for the future chemistry courses. That's why I encourage you to make study guide. I encourage you to solve the sample exercises and then do the exam correction so that I can help you guys get prepared, the study habit, study method to be successful for the future chemistry course. Okay, so don't focus too much on getting higher grade. Try to focus on developing a good study method, effective study method. Okay, so again, if you want to talk to me more detail about this study method, stop by on Friday, have a quick chat with me. So that's that about exam 2. By tomorrow, I should be able to post the midterm grade. Okay, so that April 1st, I believe April 1st is April 1st is drop date. Okay, so I will try my best to finish posting midterm grade by Thursday morning at least. Okay, I haven't finished grading exam correction yet. It's taking a lot of time for me, so I will try my best to finish grading by tomorrow night. If not, latest Thursday morning, so that you guys can decide whether you want to stick with the course or not. Friday, so the drop date, you will have option to drop this course or continue this course. Okay. All right, so that's that. Let's move on to chapter 19. Any questions about exam 2 correction, or extra credits, study guide, midterm grade? Any questions? Okay. There's no more question. Let's move on to chapter 19. In this chapter, we will be learning about chemical thermodynamics. We will be learning about entropy and the second and third law of thermodynamics. Okay, so we'll be learning about entropy changes in chemical reactions, Gibbs energy, etc. So thermodynamics. Thermodynamics in general is a study of relationship between heat, energy, and work. Okay. Heat or energy and work. Okay. And if you can recall from General Chemistry 1 course, in chapter 5, you've learned about thermochemistry. You've learned about energy, you've learned about the first law of thermodynamics and the concepts of enthalpy, if you can recall. Hopefully you guys can recall. In chapter 5, the first law of thermodynamics was introduced, which states that energy can neither be created nor destroyed. And you've also learned that energy can be converted from one form to another form. Energy can be transferred from a system to surroundings or surrounding to a system. Okay, hopefully you guys can recall this. In this chapter, in chapter 5, you learn about enthalpy. In this chapter, we will be learning about second and third law of thermodynamics and then the concept of entropy. Okay. This is what we're going to be learning in this chapter. So what is the difference between enthalpy that you're learning in chapter 5 and entropy that you will be learning in this chapter? Enthalpy and entropy are both part of thermodynamic system. However, they are two totally different concepts. Okay? Enthalpy is the heat absorbed by a system during a constant pressure process. Enthalpy. Okay? Enthalpy is basically amount of internal energy contained in a compound. Heat content of a system. Entropy Entropy is a measure of the randomness in a system, or entropy is a measure of a disorder in a system. So entropy is the amount of intrinsic disorder within a compound. Okay, so state of disorder of system. Okay, they are different. So both enthalpy and entropy play a significant role in determining whether a process is spontaneous or not. Okay, they both play a role. Along in this chapter, we will learn how enthalpy and entropy both are related to spontaneity of a process. Okay, so what is a spontaneous process and why do we care? Spontaneous processes are any process that occurs on its own without any outside assistance. Okay. So spontaneous means doesn't need any outside source of energy, outside assistance or outside source of energy, okay, to proceed. Okay, it doesn't need any outside source of energy to proceed. For example, if you drop an egg, drop eggs from your hands, and egg breaks. This is a spontaneous process. Objects roll downhill is a spontaneous system. Okay, when temperature is above 0 degrees Celsius, water the temperature is above 0 degrees Celsius, ice melts. Ice melts naturally. This is a spontaneous system. Okay. When temperature is below 0 degrees Celsius, what's going to happen? Water freezes. Naturally, without applying any energy. Okay, so this is a spontaneous process. You don't have to do anything for this spontaneous process. They will occur naturally without any help. Okay, and then another thing is that these spontaneous process, they are non-spontaneous in the reverse direction. Okay, so dropping an egg break, it's a spontaneous process, but the reverse process is not spontaneous. Okay, so objects do not roll uphill spontaneously, right? Object roll downhill spontaneously, but it will not roll uphill spontaneously. When temperature is above 0 degrees Celsius, water will never become ice. Okay, that's a non-spontaneous process. Okay, we should not confuse spontaneous process with fast process. Okay, spontaneous process can occur fast or slow. Okay, fast or slow. And also, non-spontaneous doesn't mean it's impossible. Okay, object rolling uphill, for example, is non-spontaneous. But is it impossible? No, it is possible. If you put energy, it is still possible. Okay, so non-spontaneous doesn't mean it's impossible. Okay. Here's a diagram showing how ice melts into water at temperature above 0 degrees Celsius. So temperature above 0 degrees Celsius, ice will spontaneously melt into water. Okay, at temperature below 0 degrees Celsius, what's going to happen? Water will naturally, spontaneously freeze into ice. So when someone asks you whether ice melting into water is spontaneous or not, you have to say, I don't know. You need to immediately ask, what temperature are you talking about? Okay, because at above 0 degrees Celsius, ice melting is spontaneous. However, below 0 degrees Celsius, is ice melting spontaneous? It is not spontaneous. Ice melting is spontaneous. However, temperature below 0 degrees Celsius, ice melting is non-spontaneous. Okay, let's try a sample exercise. Predict whether each process is spontaneous as described. Spontaneous in the reverse direction or at equilibrium. A, water at 40 degrees Celsius gets hotter when a piece of metal heated to 150 degrees Celsius is added. So for A, the heat is transferred from hot metal to water. So this is a process that will occur without any extra help. Okay, so heat transfer from hotter object to cooler object will occur naturally, so this is a spontaneous process. Heat transfer from hot metal to cooler water is spontaneous. Okay, so for B, water at room temperature decomposes into hydrogen and oxygen gas. So have you ever seen water bubbling into gases all of a sudden? No, right? Water in a jar will remain as it is even hundreds of years if it's in a cool system, right? Water can evaporate, but decomposition of water into hydrogen and oxygen gases definitely don't occur naturally, okay? This is a non-spontaneous process. Okay. So for C, benzene vapor at pressure 1 atmospheric pressure condenses to liquid benzene at the normal boiling point of benzene, 88.1 degrees Celsius. Okay, so this is a question asking whether vapor will condense into liquid or not. Vapor condense into liquid or not. So since boiling point of benzene is 80 degrees Celsius, since boiling point of benzene is 86 degrees Celsius, if your temperature is above 80 degrees Celsius, what's going to happen? The liquid will evaporate, okay? How about temperature below boiling point? The liquid will sorry, the vapor will condense into liquid. Okay, so at what condition the vapor will condense into liquid naturally, spontaneously? It's going to be at this temperature. Okay, at this temperature, the vapor will condense into liquid, because that's going to be a spontaneous process. Okay, how about temperature higher than 80 degrees Celsius? Will this occur spontaneously? No. At this temperature, this process is going to be considered as a non-spontaneous process. Okay, at this temperature, only liquid evaporating into vapor is going to be considered as a spontaneous process. Okay. Any question for this slide? Do you need more? Anybody need more time?
Can you say that last part you just said again?
You want me to repeat what I just said?
Yeah, please.
Okay, so at temperature lower than boiling point, the vapor condenses into liquid. This is a natural, spontaneous process. Do you agree with that? And then at temperature higher than boiling point, liquid evaporate into vapor. Just like if you are boiling water, if your temperature is higher than boiling point of water, which is 100 degrees Celsius, then the water liquid will spontaneously evaporate into water vapor, right? So similar idea. If the temperature of the system is higher than 80 degrees Celsius, the boiling point, then the liquid will evaporate and it will turn into vapor. This is a spontaneous process. Okay, but this process is spontaneous at this temperature. But is this process also spontaneous at this temperature? The answer is no. At this temperature, a temperature lower than 80 degrees Celsius, lower than the boiling point, the liquid will never evaporate into vapor naturally, spontaneously. Does that make sense?
Yes.
And the same idea. At temperature higher than the boiling point, the vapor will never condense into liquid. Only when temperature is lower than boiling point, the vapor will naturally, spontaneously condense into liquid. Okay? All right. So we have looked at spontaneous and non-spontaneous process. Now we will learn about reversible and irreversible process. So reversible process is a process that both system and surroundings can return to exactly the states they were in originally by following the reverse path. Okay. Irreversible process is a process that system and surroundings cannot return to exactly the states they were in originally. Okay. So those are the differences. I'm going to write that down. Reversible. Process both system and surroundings can return to exactly the same states they were in originally. By following the reverse path. Okay, and irreversible process is going to be a process that both system and surroundings cannot return to exactly the same states they were in originally by following the reverse path. Okay, so when two objects with different temperatures are placed together, just like the sample exercise question B in the previous slide, where hot metal was submerged in water, the heat will flow spontaneously from hot metal to water, right? Cool water. Heat will flow naturally from hot metal to cool water, right? The heat, can heat flow from cooler water to hot metal? It is impossible to make the heat flow in the opposite direction from cooler water to hotter water. So this is an irreversible process. Okay. However, there is an exceptional case where heat transfer can be reversible. Okay. So heat transfer is normally irreversible. But heat transfer can be reversible in special situations. Okay, when system and surroundings have infinitesimally small, extremely small difference in temperature, then the flow of heat can actually be reversible. Okay, so let's consider the situation where system and surroundings have equal same temperatures. So they basically system temperature, surrounding temperature, they're basically the same, the equal temperature. If you increase small, extremely small amount of temperature of the system, then extremely tiny bit of heat will be transferred from system to surroundings. Okay, you are at equal temperature, but if extremely small amount of temperature of the system, if you decrease the extremely small amount of temperature of the system, then that tiny bit of heat will be transferred from surroundings to the system. Okay, because extremely small, a negligible amount of change in temperature is made, we can still consider this process reversible. Okay, since we made extremely small or negligible change in temperature, we consider this as no change. Okay, so again, the definition of reversible process is a process that can be restored to original condition with no change to the surroundings, right? The key to the reversible process is no change, okay? But if the temperature change, if you're changing a temperature, right? If the changing in temperature is infinitesimally small, negligibly small, then it can be considered as no change, okay? So the example will be converting between ice and water. Converting between ice and water at 0 degrees Celsius, basically equal temperature. Okay, the heat transfer between ice and water at 0 degrees Celsius is considered reversible process. Okay, so within very small plus and minus between 0 degrees Celsius, we consider that as reversible process. Okay, so if the question asks whether a heat transfer process is reversible or not, you have to say it depends. If the change in temperature is very extremely small, negligible, it is considered a reversible process. Heat flow, the key takeaway from this slide is the heat flow is only reversible if the temperature between the system and surrounding is infinitesimally, extremely small. Okay, I'm going to write that down. I'll put it here. Okay. Heat flow is only reversible if temperature difference between system and surrounding is extremely small. Okay, infinitesimally small. Infinitesimally small. Okay, so again, that was a reversible process. And let's take a look at irreversible process. Let me repeat the definition of the irreversible process. Irreversible process is a process that cannot be undone by reversing the change to the system. Okay, so irreversible process is a process that system and surroundings cannot return to exactly the state they were in. Okay, I'm going to write that down. irreversible process is a process that system and surroundings cannot return to exactly the states they were in by following the reverse path. Okay, so let's take a look at diagram here. This diagram shows an irreversible process. Okay, let's say you have a gas filled up in a cylinder, okay, here, and a wall is there to hold the gas in the right side of the cylinder. Okay, if you remove this wall, the gas molecule will naturally flow to fill up the whole entire cylinder. So there is no work done by the system to make this gas flow. The gas will flow naturally. You don't have to input any energy to make this gas flow. It will flow the rest of the cylinder naturally. Okay. So how can we achieve the original state? This is the original state. How can we achieve the original state, the divided state? In order to achieve this original state, this is original state. In order to reach the original state, the divided state, we need to some work. We need to use the piston to compress the gas. Okay, since going back to original state requires work, same path doesn't work. This path required 0 work. But in order to go back to this, you can't go back to the original state by following the reverse path. Reverse path is 0 work, but with 0 work, you can never go back to the original state. Okay, so therefore, this process is considered irreversible. Okay, so to sum up the irreversible process, if work is required, okay, if energy needs to be applied to restore to the original state, then the process is considered irreversible. Okay, I'm going to write that down. If work or energy is required to achieve original state, that process is considered irreversible. Irreversible process. And all spontaneous process are irreversible because all spontaneous process require some kind of energy or work needs to be applied to go back to the original state. Okay, so that's the important key point from this slide. Spontaneous process is irreversible. Okay, why? Because all spontaneous process require some kind of work or energy that need to be applied in order to go back to the original state. So far we've learned about spontaneous, non-spontaneous process, reversible, irreversible process. We will now moving on to learning about entropy, a key concept of this chapter. Okay, so to apply what we've learned about irreversible process to predict whether a process is spontaneous or not, we need to examine a thermodynamic quantity called entropy. Okay, so what is an entropy? Entropy is commonly defined as a degree of randomness or disorder, right? But this is pretty confusing. So the better definition would be a measure of how much energy atoms and molecules become more spread out in the process. I'm going to write that down. How much energy of atoms or molecules become more spread out in a process. Okay, as you can see here, the gas molecule was confined in a certain space, but then when you remove this partition, the gas molecule naturally, spontaneously spread out, right? So how much energy of atoms and molecules become more spread out in a process, okay? Because of this spread of energy, people think of this part as a disorder, okay? The spread of energy part is what people think of it as a disorder, randomness, okay? So low entropy is energy is concentrated, okay? High entropy, energy is spread out. And entropy is a state function. Okay, what is a state function? I'm not sure if you can recall what state function is from General Chemistry 1, but state function is a type of system that doesn't depend on the path that the system took to reach the current state, the final state. Okay, so entropy is a state function. That means entropy doesn't depend on the path that the system took to reach its current state. What matters is the entropy in the initial state and final state. So how it reached the final state doesn't really matter. Okay, so the change in entropy can be found by taking the final entropy minus initial entropy. Same equation as enthalpy, right? This is what you learned in chapter 5, right? Okay, so just like enthalpy, entropy has same equation. Entropy change is going to be final entropy minus initial entropy. Okay? And for a process occur at constant temperature, change in entropy can also be found from the heat transferred in a reversible process divided by constant temperature. Okay, so for constant temperature process, okay, change in enthalpy can also be found from heat transfer in, I'm going to write this down. This is heat transferred in a reversible process divided by the constant temperature. We're dealing with a constant temperature process. Okay, so this equation can also be used for heat transfer in an irreversible process as well too. Okay, so we can label this as delta S equals Q, heat in general, divided by T. Okay, it can be used for the irreversible process too. Since we've learned that the path is not important for entropy because it's a state function, right? So let's say you have state 1 and you're going to state 2. Okay. The reversible process would have certain amount of heat transferred during this process, labeled as Q reversible, right? But even if this going from state 1 and state 2 is irreversible, even if this process is irreversible, certain amount of heat is still transferred. Okay, so that's why we can still use this equation for the irreversible process too. Okay, so we will use this equation for the general equation. Let's try a sample exercise. So okay, so I'm not sure if you can recall from chapter 5, the enthalpy is equal to heat, okay? So if anything enthalpy shows up, it's equal to the heat over here, heat part, okay? So the question says elemental mercury is a silver liquid at room temperature. Its normal freezing point is negative 38.9 degrees Celsius, and its molar enthalpy of fusion is delta H fusion equals to 2.29 kilojoule per mole. What is the entropy change of the system when 50 grams of mercury freezes at normal freezing point? Okay, so what is a enthalpy of fusion? This is basically the heat of melting. Okay, you require this amount of energy in order to melt the mercury. Okay, enthalpy change resulting from providing heat. Resulting from providing heat. Okay. Heat of fusion, heat of melting is given. However, what situation are we dealing? Are we dealing with a melting situation or freezing situation? We are dealing with a freezing situation over here. Okay, so if the heat of melting is 2.29 kilojoule per mole, freezing should have opposite enthalpy, right? So the freezing process should have negative heat of fusion, which is negative 2.29 kilojoule per mole. Negative sign. Okay. And then we are also given molar enthalpy of fusion. Molar enthalpy of fusion. Okay, that means in order to melt one mole of mercury, you need 2.29 kilojoule of energy. Okay, in order to freeze 1 mole of mercury, you need negative 2.29 kilojoule of energy. Okay, but how many mole do you have? You have 50 gram. Okay, we don't know how many mole this 50 gram is, so let's try to convert this into mole. Okay, so 50, we have 50 grams of mercury, which is equals to 50 gram divided by molecular weight of mercury from periodic table is 200.59 gram per mole. Gram cancels, you're going to left with mole equals to 0.249 mole. So now we have all the information we need. We know that 1 mole of mercury requires this amount of energy to freeze 1 mole of mercury. You have this amount of mercury. So then how much energy do you need to freeze this amount of mercury? You need to multiply. 0.249 mole times negative 2.29 kilojoule per mole. Mole cancels equals to negative 0.570 kilojoule or negative 570 joule. So what does this amount of energy tell you? This tells you that you need this amount of energy to freeze 0.249 mole of mercury. Okay, so the question is asking the entropy change. Okay, so in order to find the entropy change, we're going to use the equation that we learned in the previous slide. Okay, so the entropy change of the system equals to heat divided by temperature. Okay, the heat requires is -570 joule. Temperature is in Celsius. We need to convert this into, another note here is that the temperature has to be in Kelvin. Kelvin, okay? This is very, very important. So if we convert this into Kelvin, we get 234.3 Kelvin. Okay, so if we divide by 234.3 Kelvin, we get -2.44 joule per Kelvin. This is the final entropy change of the system by freezing 0.249 mole of mercury. Okay, I'm going to repeat that one more time. This is the -2.44 joule per Kelvin is the entropy change of the system when you freeze 0.249 mole of mercury. Okay. So that's the end for today's lecture. Okay, I'm going to hang around for another 5-10 minutes just in case anybody have question. If you don't have any question, feel free to leave the meeting, and I'll see you guys on Thursday. Okay.
Professor, one question.
Mhm.
Do you teach organic chemistry or will you next semester?
Organic chemistry? No, I'm not. I'm not teaching organic chemistry next semester.
Oh, okay, thank you.
Mhm. I will only be teaching general chemistry 1 classes next semester. So, yeah, I guess none of you guys need to take Gen Chem 1 again, but yeah, I'm going to teach 2 of the Gen Chem 1 classes next semester.